Have you ever wondered why it's crucial to evaluate machine learning algorithms? Well, let's dive into it. When we train a machine learning model, we're trying to make it as accurate as possible. But how do we know if our model is truly reliable? This is where the concept of testing our model comes into play. We test our models using datasets that were not used during the training process, thus providing an unbiased evaluation of the model's performance. One such technique is the leave one out cross-validation, or LOOCV. It's a procedure used to estimate the performance of machine learning algorithms. Although it can be computationally expensive, it gives us a reliable and unbiased estimate of our model's performance. It's particularly useful when we have a small dataset, or when an accurate estimate of model performance is more important than the computational cost of the method. Understanding the essence of evaluating machine learning algorithms is the first step towards improving the accuracy of your models. Now, how does the leave one out cross-validation work? This question introduces us to the second scene: LOOCV model evaluation. LOOCV is a special configuration of k-fold cross-validation where k equals the number of examples in the dataset. This means that if you have 100 examples, you would end up creating and evaluating 100 separate models. The advantage of this approach is that it offers a robust estimate of model performance, as each row of data gets an opportunity to be a part of the test set. However, this brings us to the major downside of LOOCV. It's computationally expensive. Each additional example in your dataset means an additional model to be created and evaluated, which can be a significant undertaking depending on the size of your dataset and the complexity of your model. So, while LOOCV might be computationally expensive, it provides a reliable and unbiased estimate of a model's performance. Are you curious about how to perform the LOOCV procedure using the Scikit-Let machine learning library? Well, let's dive into the process together. To get started, you'll need to import the necessary libraries. We'll be using pandas for data handling, NumPy for numerical operations, and of course, Scikit-Let. Now, Scikit-Let offers a function named leave one out, which simplifies our task. First, prepare your dataset. Once that's done, create an instance of the leave one out function. This instance acts as our cross-validator. The beauty of this function is its simplicity. There's no need to specify any parameters. It automatically sets the number of splits equal to the number of samples in your dataset. Next, use the split function to generate indices for splitting your data into training and test set. It's a neat way of handling the partition. Finally, fit your model on the training set and evaluate its performance on the test set. With the help of Scikit-Let, performing the LOOCV procedure becomes a piece of cake. But how can we use LOOCV to evaluate machine learning models for both classification and regression, you may ask? Well, let's delve into it. In classification, LOOCV helps us to evaluate how well our model can predict discrete categories. It does this by training the model on all data points except one, making a prediction for the excluded data point, and then comparing it to its actual category. This process is repeated for each data point, providing a comprehensive performance assessment. On the other hand, in a regression context, LOOCV assesses how accurately our model can predict continuous values. The process is similar to classification, but instead of comparing predicted categories, we're comparing predicted numerical values to the actual numbers. The key difference between the two lies in what they predict: categories for classification and numerical values for regression. And there you have it. With LOOCV, you can evaluate the performance of machine learning algorithms for both classification and regression.